So the last major force that we're going to deal with is tension. Okay? And this is anytime you have an object that's suspended from a rope or a chain or a rod or a cable or anything of that ilk. Okay? You're going to find that while the names of these forces change and while they're used in slightly different circumstances, the game is the same, guys. The game is always the same. You draw a free body diagram, you set up your Newton's second law equations, and you solve for what you're looking for. Okay? So don't let the sheer quantity of the number of different forces that we're dealing with feel like a confusing thing or feel like like an overwhelming thing. Just always remember that if you follow the simple steps of creating a free body diagram, finding the direction of your forces, breaking them up into components, and then substituting into your Newton's second law equations, you'll always get the answer. Okay? And that is what I want to prove to you here with tension. And so we're here at the tension slide that shows various different types of tension. You guys can explore those different pictures. But I want to start by looking at this problem about some hanging insects. Okay? So the question is, if you go to the hanging insect slide, some insects can walk below a thin rod, such as a twig, by hanging from it. Suppose that such an insect has a massive M and hangs from a horizontal rod as shown in the figure, in this little picture that I drew here, with an angle of 40 degrees. Its 6 legs are all under the same tension and the leg sections nearest the body are horizontal. What is the ratio of the tension in each tibia, meaning the legs, right, to the insect's whole weight? So the ratio of the tension in each leg to the insect's whole weight. In other words, how much of the weight does each leg have to support? Okay? All right. Let's take a look at this. So no big surprise. We're going to do the same thing we always do, which is make a free body diagram. Okay? What is happening in this free body diagram? Well, we have the little twig right here. Okay? And then we have the bug. Okay, there's little antennae, right? And then he has these legs that go like this, right? And there's 6 of them, okay? And the angle for each one is 40 degrees. That's 40 degrees as well, okay? So the tension in each tibia, this is the T here. This is the T, okay? There is tension pulling this guy up in this direction, right? So if I draw the free body diagram, I'll make it a different color, right? This is like tension in this direction and tension in this direction, right? That is what this guy's experiencing. And what else should be in this free body diagram? Well, he's got a weight. We can't forget that he's got a weight, right? And we know that those 6 tensions, right, the y component of those 6 tensions, because remember, this guy's going to break up into a ty here and a tx here, right? And then a ty here and a tx here. But remember, again, there's 6 of these ty's because there's 6 legs, right? These 6 ty's are going to have to exactly cancel out this w. But let's prove that, right? Let's go ahead and say, summation of forces in x equals max, and summation of forces in y equals may. All right? Okay, summation of forces in x. Well, here's the thing. I got 3 tx's going to the right? And then I got 3 tx's going to the left, right? The x component of this guy's legs are pointing this way for everything on this side of his body, and everything on this side of his body, the tx's are pointing this way. So I have 3tx minus 3tx equals, is he accelerating in either direction? No. So we know that this is 0, right? So this just gives us 0 equals 0. Boring, all right? Doesn't really tell us anything. Boring equation. Let's go to the more juicy one. Let's go to the summation of forces in y, okay? Well, what do we got going on in positive y? We have this ty, 3 on this side, this ty, 3 of those on this side, for a grand total of 6 ty, right? And what's going in the negative direction? W, which is just mg, right? So 6ty minus mg equals, now what is the acceleration in the y direction? hey, he's just minding his own business, hanging there from this little twig, okay? Is he shooting up in the air? No. Is he falling down? No. He's just hovering here on his little twig. That must be 0, right? Which means that 6ty is just equal to mg. True story? Okay. Now, we need to remind ourselves, what is ty? Well, ty is going to be the sine component of this angle, right? The sine component of this vector, but since this component is not actually touching the 40 degrees, it gets the sine, not the cosine. So this actually becomes 6t sine theta equals mg. Okay? And so this is much more interesting. This is a good place to pause and ask ourselves, what are we actually looking for here? Okay? What we're looking for is the ratio of the tension in each tibia, that's T, right, to the insect's weight, that's mg. Okay? So I'm actually looking for T over mg here, right? That's what I'm solving for. This is my big question mark. Okay, so let's do that. Let's bring this guy over. So I get T over mg, right? And then I divide the 6 sine theta over here, right? And so I get 1 over 6 sine theta. Okay? Now, we have our answer, okay? If we just take 1 divided by 6 times sine of 40, we get that ratio. And I encourage you guys to plug in that number and get that ratio. But one thing to note, this ratio will change depending on what angle he's holding himself up at, right? So there's going to be, like the amount of tension that he feels, that each little guy feels is going to depend on what that angle is, right? But the bottom line is, that is our ratio, right? This tells us how much weight each of those little tibias is going to have to handle.